The future is watching. Welcome to OpCode Virtual Summit.
Okay, hey, thank you, Matt. Thanks for hosting us in OpCode. Hi, everybody, thanks for showing up. That is our first experience as speaker on a full virtual event. We hope everything will work smooth, but the crash is just beyond the edge. In this presentation, we will show our deep analysis on APT Linux vector, that for us is not so common, hoping that will help other researching that will find something similar and add to deal with. So let's introduce ourselves. My name is Silvio Porta. I work as a senior architect in Leonardo Cybersecurity Research Center. Leonardo is an Italian multinational company specialized in aerospace and defense and security. It is the 8th largest defense contractor in the world. The company is organized in divisions such as helicopter, aircraft, aerostructures, electronics, and cybersecurity. One of our duty is to design advanced detection system for customers. For this reason, we continue to study complex attacks. Previously, I worked in Dell EMC as a security researcher and for Symantec as malware reverse engineer. I hold a PhD in network security. So, Antonio, take the floor.
Hi, everybody. This is Antonio. I'm working for Leonardo Cybersecurity Division 2 as a senior architect. I've been an academic researcher for a while, and then I moved to more technical stuff, working as a cyber threat analyst for various customers. I just want to remember that this is a joint work with our colleague, Nino Verde, which work with us in our group.
Okay, so let's go ahead. What we are doing here, we basically on April, during our hunting activity, we find a couple of samples of a Linux backdoor that trigger our interest with really few detection, between 10 and 20 at a time. We started to analyze it and we found that there are some reports talking about something similar to it. This sample seems to belong to Turla, which is one of the most advanced APT in the world that has been operational since 2004, I think. It is really famous for developing a new and very advanced technique to avoid detection to ensure persistence on the network. The most famous is the Epic Turla, where they use the satellite channel to connect the CTU with the malwares. Turla is known for targeting, among the others, government, defense, Ministry of Foreign Affairs, educational sector, and all around the globe. Our story really started a long time ago. It is a story of a well-engineered backdoor, I think, that in the time had not changed so much. So the first report talking about it is from Kaspersky. It is from 2014. Mr. Kostin and Kurt are the authors of it. It talks about a Linux passive vector which use pickup filter to intercept the traffic. After, on 2016, come out from Cert Milani, the RUAG report, which is a complete picture of the Turla threat actor activity, and it has some reference to a Linux vector, which also has some remote file system capability. And that is our Penguin as well. On 2017, for the security summit analyst, Kostin with Thomas and Kwan described maybe the oldest and longest cybersecurity operation in which take apart our Penguin as well. And the last but not least, at the end of the 2017, Kwan, yes, there is always a Kwan story beyond, give on Twitter a Christmas Turla present talking about a new version with a Chrome binary embed. The Chrome binary is really important to construct the timeline. It is the legitimate Chrome binary. Antonio will talk more later. In those reports are described what we call Penguin 86 and Penguin 2. In our report that came out at the beginning of May, we found we will describe the new sample that we called we named it the Penguin 64. That is the star of this presentation. Come out, Penguin. It's here. So go ahead. So the agenda is really dense. We have limited time. We will try to stay in. Indeed, Antonio will show now how to build a timeline for the Penquin sample. After, I will describe the Penquin commonalities and difference, showing the main commands and features. Following, we will show how to build a magic packet, and we will conclude with a couple of things. So let's go on.
Okay, with such a complex threat landscape, the first problem that we had was to place our sample in a timeline. One thing to remember is that we are looking at ELF files which do not have a specific compile timestamp that can be used as a starting point for the analysis, as it happened, for instance, for Windows executable. And since we are not a world-class Linux investigator, we proceeded with a trial and error process. Our starting hypothesis was that some of our samples were more recent than the one documented by Kaspersky in 2014, mainly due to the first seen date on VirusTotal. So to verify this hypothesis, we went through 3 different approaches: ABI version, statically linked libraries, and embedded binary analysis. So let's start with the ABI version, which is related with the kernel version. It is stored as an ELF note within the .note ABI tag field. This information can be extracted with tools such as SplitElf if you know where to look, or you can use even Python libraries such as PyElf tool to parse ELF sections. The table in the slides shows the ABI information for all Penguin version. As you can see, the most recent one is the 64-bit version. So we tried to answer to the question when binaries with such ABI were being built in the past. And we looked at several GCC releases, and we went back up to 2006, here when GCC 346 was released. We were still far from the version of the Penguin, since the ABI in that case was 2.6, and we needed 2.4 at least. But one thing became clear at that point, is we could not expect a fine-grained information from such analysis, since the ABI seems to remain quite stable across the years. It remains stable for a couple of years at least. However, we decided to look at the Linux kernel version release date directly, and we got very old time references that were pointing us to the early 2000 period, which I have to remember is 20 years from now. And just to make sure that you guys get how far in time we are, this is the console from the Space Shuttle of 2000 compared with the console of SpaceX of 2020. And you can see that a lot of improvement have been done in 20 years. But also, to be even more clear, here is the Gladiator from 2000 compared with the Gladiator from 2020, which it's definitely a lot of time, you know. Okay. After we become aware of this, we decided to take a different approach. We tried with the version of the embedded static libraries, and this point lasts to our more recent period. Indeed, if we focus on the OpenSSL version, we find that the Penguin 64 bits embed the OpenSSL 101, which was released in 2014. And 2014 is also the year of the Kaspersky report. So this smells like the Turla guys decided to make a retooling during that year. And also, they probably were forced to update even the compiler to statically link the new OpenSSL version. This could be one possible reason why we see an updated ABI, but this is just an hypothesis. The last approach can only be used with the 64-bit versions because it is based on the embedded cron binaries that Silvio described before. We found 3 different versions of the 64-bit Penguin, and each version was embedding a different cron binaries. So our observation here was that since they were all clean and legitimate binaries, they had to belong to a specific Linux distribution. Another possible hypothesis, of course, could be that the threat actor built this tool by himself. However, we were lucky since we were able to find these builds inside 2 different distributions that are CentOS and Ubuntu. And during this analysis, we learned that a different release of a given Linux distribution may actually embed the same build of the binary utils, such as cron. That's why we can only detect a time range that, once again, is more recent than the one that we found with OpenSSL, since one of the cron was pointing us at up to 2017. And this was the best estimation that we were able to do with the information in our hands.
So just comparing the three versions of Penguin, the code is basically the same. The size of the code is really bigger. We are talking about 1.5 megabyte for the Penguin 64, and between 600 and 800 kilobytes for the first two versions. The size of the code is so big because the Turla compiled statically different libraries inside the Penguins, such as OpenSSL, libc6, and the pickup filter as well. So what are the differences of the three versions? The three version has more or less the same code, slightly different for the last version where they try to hide some strings and remove some, I think, signature on it. The first version, the Penguin 86, is a passive backdoor, so it just wait for an activation packet that comes from the network to start this activity. It needs two parameters from command line to work properly, that are the ID and the interface where to listening. I will talk more about the ID later. And it uses a command function to process the CPU that received the data. So the Penguin 2 is active. It is more classical backdoor. It has a hard-coded IP at the end of the file that during the init phase will be extracted, and it will start to beaconing to the CPU. And it also uses the same command function to process the data received from the CPU. It is the only Penguin that does not require the root privileges, because it does not use a root folder for its activity. The last version that is our star, the Penguin 64, is passive as the first one, but it has encoded the ID interface parameter directly on the sample, which is 29 for the ID and the interface ATH0, for example. It drop and run cron, and after remove the file from the file system in the root folder as .sys file. And it uses a different function as main that we call the callback. One other stuff to say is that the Penguin 2 is some of the sample of Penguin 2 are not stripped, so we can extract the name of the function that the attacker give in the code. So let's give a look to the code, and what we have is, for example, there is an happy string. That is, our Penguin are really happy. This string in the old Penguin is just hard-coded and put inside the function of upload and download. In the new Penguin, they are stacked strings. So the attacker changed it maybe to remove a signature, a string signature on the sample. Another important stuff, another example could be the ID code. So this code is used to process the ID that in the old Penguin is given from the command line, and this number will be used to calculate the first part of the network pickup filter used to validate the packet. So if you give to the old Penguin the value that is hard-coded on the new Penguin, that is 29, as I said, it will generate the same part of the filter. So as you can see from the code is do exactly the same stuff. Just it is maybe rearranged for compilation in the new architecture version. So go ahead and give a look to the command function that is the main function used for the first two versions of the Penguin. This function is put inside a loop that is used to process the data received from CPU. One of the parameters that this function needs to work is the CMD tab data structure, which is a table that has a column with strings and another column with with functions, and the 30 column is contain the number of minimum and maximum parameter allowed. So how does it work? Basically, the function will, the malware will extract from the from what is receiving from the CTO a string, and if the string match one of the string present on the first column, it will execute the corresponding function, double checking that the minimum and the maximum number of parameters are exactly the one specified in the last column. So the reference to this function in the first two versions of Penquin are 3. On the new version became 2 because the 64 it is removed from the main. Okay. So give a look to the inside the command function. I say that what I already described is the try built-in function. It gets the CMT tab structure and execute the corresponding command. If the string does not match any of the string of the table, it will consider it as a shell command, and it will execute directly through the bin.sh, giving storing the output in another file. So going instead to the do callback function, this function is not present on the Penguin 2.0. So because probably it wasn't the time to put there. It is present, but in the oldest Penguin and the new Penguin. As you can see, the function is more or less the same. They changed the name where the file used. So this function, what does is after the sample receive the activation packet, he expects that the CTO send back a file to him that it will receive it as .session file inside the root folder. After save the file, the malware will change the directory and go to the root directory, and will call another function that we named UU decode. When we started to reverse this function, we thought that it was a new encoding schema that the Turla guys created for this sample particularly. But looking at the code structure, looking the difference between the code of the malware and this part of the code, we just started to think that there should be something else. And we try to find some reference online or something similar. And digging, we find this utility that is called UU encode. It is one of the utility present in the oldest Linux version, which was used to transmit a binary file over a medium that does not support anything else than hashing. It supports basically a two encode schema, that is the UU encoding and the base64 encoding. So looking at the code, another assumption that we made is about the next file, that is the HS_perf data for the new version. So, and what we thought is that the UU encode create a sort of archive, and inside the archive, the malware expect that the file extracted from the archive, it is called the HS_perf data, and this file should have the correct execution flag inside. After that, the .session file, the UU encoded file, will be removed, so it will be deleted from the disk, and will be executed the new file extracted from that. The output will be saved in a storage string. So that is the callback function. As I said, the sample has the same code base. So all the sample has all the version of Penguin has all the same functionality and capability. On the left side of the slide, we have all the classical canonical backdoor functionality, such as download, upload, remote execution, and so on. On the left side, we have some particular functions that are used to manage a remote file system. These functions start all with do_yes. And this function works all at the same way. So for example, giving the vstat function, The operator sends to the Penguin, after the connection is established, this command passing a target IP. The Penguin will extract this target IP and establish a new connection to the peer, passing directly the code of the command, in this case 15 in hexadecimal, and the target IP will reply with the information necessary to complete correctly the command. In this case, the file system type and the free disk space. The Penguin will close this connection and send back to the operator a string, a wrapped string with this information inside, such as WES file system type and the free space, available space. And it will close the communication with the peer and waiting for the next command from the operator. Okay.
Okay. Now we are ready to introduce the activation packet. So let's start with the scenario. We have an operator controlling two host directory that are host A and host B. Host B is listening for incoming connection on port XYZ. Then we have the Penguin Linux box, which is in a passive state still. In order to activate the Penguin, host A sends a specific packet to the Penguin saying, "Hey Penguin, please connect to host B on port XYZ. This is the packet signature." The Linux kernel reply with a reset or an ICMP message depending on the transport protocol of the incoming packet. But since this is not a normal packet, but this is a magic packet, the Penguin, which is looking for the incoming traffic, sniff the packet, verify the signature, and follow the instructions specified in the payload, and establish a TCP connection to host B on port XYZ, and then the communication starts. So in order to make the Penguin happy, you have to craft a packet that respects some rules. The first rule is the pickup rule. The magic packet can be any TCP or UDP packet that match the filter represented in the slide. This filter is encrypted and statically embedded within the sample. For UDP packet, the filter means that the second D word of the payload must match the filter. That is starting at offset 12, the next 4 byte masked with E007 FFFF must be equal to 6005 BDBD. For the TCP packet, the filter is checked against the ACK number since it starts at offset 8. And that's it. Just we have to add a different version of Penguin, have different constant values. For instance, for the 32-bit, we have the BEBE instead of BDBD as a mask. The second rule is more a rule set and is a bit more tricky than the first one. I have to say that it was a real pain actually to understand. There are several bit masks that are applied to the first and the second D word of the incoming data. So in detail, the schema can be represented with data on top and condition at the bottom. The input to the transform function are the two D words represented here and the source port of the packet. Due to the pickup rule, some bits of the second D word have fixed values, while other, which are the ones that are masked by the pickup filter, can get arbitrary values. The transformation combines inputs bit to derive the final destination IP as represented in the slide. So we have 24 bits coming from the first D word directory, 4 bits that are grabbed from the second D word, and the final 4 bits that are taken from the source port and placed at predefined position. However, in order to create a well-formed packet, there are other conditions, several conditions that must be met, as represented in the bottom of the slide. Pieces of input data are combined in a Boolean expression. Colors let you easily see how each piece of the input is used in the condition checks. If the expression is satisfied, then you are almost good to go, since there is one more thing that you have to take care, but we will see it in a moment. One thing to note here is that most of the bit transformation does not align to byte boundaries, and this could have been done on purpose just to slow down the analysis. Another thing is that the 16-bit value coming from the concatenation of N3 with N6 is used as the destination port for the new connection, that is what I'm saying, will be always a TCP connection, regardless if the packet activation is sent via UDP or TCP. So there is this last thing you have to consider, which is the internal status flag of the Penguin. Indeed, you have two possible activation packets, even if this is a 2-bit value, which potentially allows 4 different states. We were able only to get 2 values that are 0 or 2. When the Penguin started, its status is 0. Whenever the Penguin receives a performer packet, it toggles its state and perform the required action. Okay, but now on, it will ignore packets with the same status flag. So if you send again the same packet, it will not trigger any action. Okay, this is the setup for the demo. Host A gets IP.1, the Penguin gets IP.130, and the host B get IP128. Host B is listening to 2 different ports. Since we are testing both UDP and TCP packets and both the status flag, 0 and 2. Okay, this is the demo setup. On the top left, we have Penguin x64, which is a virtual machine that we are infecting. On the right, there is a packet sniffer, Wireshark. On the bottom left, we have the host B, which is listening to the 2 different ports. And then we are also ready to send packet on the bottom right. So we just started the Penguin here. We are just verifying that everything is okay. We can see that there are 2 processes running because one of the 2 is the legitimate cron binary. Now we are ready to send packet. We send the first packet. We can see that we sent an UDP packet and received an ECMP destination reachable message from the Linux kernel, but immediately after there is a TCP connection triggering towards the host B on the expected port. Now we send the TCP test packets. Again, we can see that we receive a reset in this case according to the protocol definition, and we verify that everything is working okay because we have 4 processes running and we know that there is 1 process for each connection. We keep going here, we send other packets, and we see that the Penguin is replying to us as expected. Again, we keep going, we send the last packet on UDP, we get a new scene back, and we verify that now we have 6 processes running as expected because we just triggered 6 different connections. And now, if we close the connection, we just will go back to the virtual machine. And we verify that we got back to the initial condition as expected because we have just 2 processes running. Okay. But we went a bit farther as, okay, we here have the same setup. So we run again, we infect the machine. We verify that everything is okay. Okay. Then here we have host B ready to accept connection. Okay, then we send the probe and we get a X calculator inside the Penguin virtual machine, which is working smoothly. You can do all fancy stuff that you can do with calculator. And if you look at the PS3, looking for Penguin, you can see that actually there is an HS perf data running, which has been executed by an SH from the Penguin x64 binary process. Sorry.
So we did that just to verify that our hypothesis on the UN code and the final file was correct, and seems that we had the right. So that concludes our presentation. If there are any questions, we are open.
Thanks for the presentation, guys. It was pretty good. While we're waiting for the chat to get ready for some more questions, so just I want to give a small reminder, like don't forget to send me your slides after so I can purge them on the GitHub. I was just talking with Yarden about it now. I dropped the link in our chat. So far, yeah. So there's Jeremy on the chat saying great presentation, guys.
Thank you.
Thank you.
And let's check if there's any question. I don't think there is. There's two good comments. People saying well played, great. I guess you explained everything so well that there is no questions. That's I think. Yeah, that's pretty much it. Well, cool. I guess I guess that that closes it. If there is no question, so that was pretty cool. So when did you guys started to analyze that malware?
A bit was at the beginning of April. We had just a sample, and our analysis take a couple of weeks, basically, more or less.
Oh wow! So it was very recently, huh? Okay,
Yeah,
okay, that's pretty cool.
Yeah. The first sample that trigger our hunting activity was yeah for the end of April.
And the report got published what, like a week ago now, I think.
It was published middle of May.
Okay, yeah, that's cool. So we have one question from the chat from Jeremy. Over what channel protocol is the file upload download occurring? HTTPS? Question mark.
The file upload download are they use they established the diffierman secure channel using diffierman, and after it was established a symmetric key that is used with Bluefish.
Okay, cool. Sounds good. Well, thanks again, guys. And looking forward getting a copy of the slides so I can reread it
Absolutely.
after.
Absolutely. Thank you very much.
Thanks again.
Thank you.